All right, good day. We are now at the last part of our root finding methods. We will have the last one, and of course, the most impactful one, the NRM or the Newton-Raphson method, right? In here, we are taking advantage of the fact that we can more easily, right? Well, easy is a vague definition, is a subjective definition, but we can easily get the tangent line of a curve using a derivative, right? If you remember last time, we were talking about the secant method, and the thing about the secant method is that, excuse me, it's easy in the sense that you can just get two values and then you can run with those two values, right? So long as you can graph a secant line between them, that'll be fine, right? With the Newton-Raphson method, you can just have one, right? You can just have one line, or rather one point, one starting point, and that will be the end of it. So long as you can graph, or rather, so long as you can get the slope of this point, which is going to be through the derivative, right? So in the Newton-Raphson method, you're going to get your original function, and you're going to derive it to get f prime of x, and you're just going to guess a certain value a, and if you substitute it to your original equation, you will get f of a. And then what you will do is that you will get the next iteration by drawing the tangent line at that point a. So in this point, let's say for example, our tangent line is going to go stretch like this. Note that in this case now, the second point that you will have is somewhere in here. Let's say for example, this is now your iteration 2, right? So this will now be letter B, maybe. Let's call it letter B. And now in here, you will have B, then f of B, right? And then how that will work, or rather the equation that gets you this next value is basically getting, right, or rather using this point and this slope, which is going to be from f prime of a, right? Notice that this is now your f prime of a. Any derivative, any value of a derivative is going to be the slope, right? And if you're going to use that point and that slope in the point slope form, what you will now get is that if you replace x with m, right, your next iteration, and then you replace your y with 0, because it's supposed to contact the x-axis, you will have this value, or rather this formula, right? It's going to be your old value minus the value of your old value all over the derivative of the old value, right? And so if you continue this graphically, what we're going to have in here is this graph of this line in here, and now you're going to see, oh, okay, it's going to contact this. Let's call it letter C, and now this letter C is going to be here, C, f of C, and then we will continue our drawing of the tangent line. Say maybe for example, going to be like this. And then note that with just 3 tangent lines, we are already way close to our answer, right? Note that now it's here, and well, it's anything after that is history, right? You have probably heard of the NRM before, the Newton-Raphson method before, right? If this is your first time using, or if this is your first time in MEADMAT, probably have heard of it somewhere before. And if this is your second time, well, this is probably the only thing you remember about MEADMAT, right? Well, now what we will do is we will solve, or we will get the roots of these equations here using the NRM, and well, our expectation is that these will be very fast, right? These will be very fast to converge, right? Let's start with x raised to 4 minus 5x plus 3 is equal to 0. That will be our f of x. That means that if we derive, this will be f prime of x is just 4x cubed minus 5, right? So let's remember those things, and then let's have them here. The NRM for 1. Everything again. JetBrains. This f of x is going to be, what was that again? X raised to 4 minus 5x plus 3. And the thing about this is that this does not need any kind of test, right? This does not need any kind of what do you call this? Any kind of logic to it. You just apply it again and again and again. It's going to be 4x cubed minus 5x minus 5. The thing with this is that the Newton-Raphson method has, I think, two main weaknesses. The first main weakness of the Newton-Raphson method is number one, well, you need to compute the derivative, right? And I know that like every equation has a derivative, but the thing about this is that you can't make a computer do this, right? Or maybe you can, right? Maybe with another kind of approximation method or an iteration. But in this case, the problem with this is that if you're trying to make a computer do this, is they can't derive, right? They can. I mean, well, maybe MATLAB can, right? But in this case, it's gonna be really difficult for you to implement a derivative, right? Now, next would be let's have what do you call this? Let's have the second what do you call this? Let's have the second problem later down the line. Let's just try and do this first, right? Let's start, I don't know, with 1, right? F prime of x, F prime of x. Let's keep going in here. And then let's have this epsilon value in here. Okay, F of x is just going to be this raised to 4 minus 5 times this value C6 plus 3. Then this will now be 4 times cubed minus 5. Then let's have our epsilon there. Okay, now this new value will be the old value minus, right? The value of the old value minus divided by the f prime. There you go. It's gonna be 0, and then we'll just drag these, and let's drag this down as well. There you go, and there it is. Right, our answer is very clear. Our answer here is very clear. This is going to be absolute value of new minus old divided by new. And yes, I know it's a division by 0 because your new value is a 0 in here, but look at that, right? With just 6 iterations, you've now gone past 10 raised to negative 7, right? So that is amazing, right? That is blazing fast, right? And again, this kind of blazing fast accuracy is inherent to the mechanics of the NRM, right? With an NRM, what you're supposed to do, or rather, it takes advantage of the fact that if you're getting nearer to your root, well, things become more of a line, right? The things approximate to become much more of a line, right? We can do this, or rather, we can show this for basically anything in here. If we zoom in close enough, this just looks like a line. And well, you can take advantage of that, right? You can take advantage of that fact, especially if you go closer and closer to any value in here. That's what you're going to create, right? Say, for example, in here, we just have this. Maybe this equation is enough. Let's just have an f of x in here, and let's hide that. And if we're going to have, I don't know, 1, then f of 1, that's going to be it. And then your next value in here would be 1 minus, right? 1 minus f1 all over f prime of 1. There you go, which is 0.8125. So let's try and continue this. 0.8125, then f of 0.8125. Then you'll now go here, right? So it's much closer, and we can continue this actually, right? 0.8125 minus f of 0.8125 all over f prime of 0.8125, and then you're already quite close to your answer, I suppose. It's now going to be let me just copy this. We can. There you go. And yeah, it's already quite close here. And if we just continue this, right? If we just continue this, well, I don't know what else to tell you, right? We can just put this minus f, this value, all over f prime of this value. You'll have basically, yeah, oh, this was our answer from before in the secant method, if I remember correctly, right? And basically, just continue an f of that. Yeah, we're already gonna have to go and zoom in quite a lot for us to get to our next value. There you go. I mean, that is the power of the NRM. And notice this only took us 1, 2, 3 iterations, and well, you're already quite close to your answer, right? In this case, it only took us what, seven iterations, and then it gave up, right? It gave up. Look at this, right? Even in this case, right? Even in this case, your f of x is already way up to 10 times negative 10 raised to negative 14, which is already so close to 0, right? Let's try another case in here. And I desperately want this to be a little bit longer, but well, what can you do, right? In this case, we will now have transcendental functions, x e raised to x e raised to x minus cosine of x. So what do you call this? The derivative for this will be a little bit more complicated, but still not that complicated, right? And here we have two functions that are multiplied together. So you will have f prime g. So f prime is just 1 in here, f prime g plus f g prime, right? G prime in here is just itself, e raised to x. And in this case, the derivative of cosine or negative cosine is positive sine. So there you go. Very easy. We can get to our answer immediately. X e raised to x minus cosine x. That is our original. This is going to be e raised to x plus x e raised to x plus sine of. There you go. There you go. And well, you can just put this in x times c6 times exponent of the c6 rather minus cosine of c. There you go. And then your f prime in here, what we can actually do is group the exponent c6 times x plus 1. So c6 plus 1 plus sine of c6. Go. We can drag this down and we can see our answer very quickly, right? At this point, at iteration 6, they're like, you know what? Never mind. At iteration 7, they're like, never mind. Okay? It's already way close enough. And that's our value, right? 5.517757. Right? Notice that after iteration 6, it is now become way lower. It is now at 10 raised to negative 8. And well, there you go. Nothing else is to be said about the Newton-Raphson method, except for now we're going to go to the disadvantages. The first one, this is the disadvantage in here. Well, it's not even that much of a disadvantage. If you're going to look at this formula, or if you're going to look at this equation, if you're going to substitute f of 0, if you're going to substitute 0 in here, you're going to create a horizontal slope, right? A horizontal slope, which means that in this case, this will divide by 0, right? Because the slope is 0, right? The f prime of that basically is going to be 0. Let's try and show this now. 0, f of 0, f prime of 0, undefined. So maybe that's one of the issues in here, but well, you're going to see this later on, or maybe you might see this behavior later on. But say, for example, we have here sine of x, right? What you're going to do is that if you're going to trace, right, tangent lines for sine of x, it will just oscillate, right? Let's say, for example, in here we have 1, and then we have sine of, f of 1. There you go. Be there. Right? And what you will do is that you will trace the tangent line there. So y times y minus f of I don't know, a, and then let's just have here f prime of a times x minus a. Let's have our a here, which is equal to 1. Ayan. So it will get this now, negative 0.55741. Right? 0. Is that 55741? This thing, let's now put it here. Okay. And what it will do is that it will now reflect it back to the other side, which is now 1.11335. Have this again, right? And then let's put this in our value of a. And then it will go here, right? To negative 1. Wait a second. Wait. Oh, never mind. Sorry. What I'm doing is a little bit wrong. But in this case now, we're going to 0.06. Okay. Never mind. We are very close to our answer already. And at that point, yeah, we kind of lost already. There it is. It is 0. But the thing about this is that there is a risk that sometimes, right, your values, or rather your iteration, may oscillate. Right? It will not give you a certain exact answer. I mean, of course, this is not going to work for stuff like pi, right? Here, pi over 2. In this case, well, this is a horizontal line, so it's not going to be very great. Maybe what about this, or something like this? It would get you to 11 point. Okay. Let's try this out now. 11.63744. Have that there. Then let's put this in here now. You're going to get here 12.9753. Okay. And then put this in here now. And yeah, going to go to 12.54914. We go back in here. Still going to go to a very particular value. It's still going to go to a root, but the thing about this is that you might have to change values, or you might have to go to a different starting point if your value tends to, or rather if your NRM tends to diverge, if it tends to oscillate between two different states. Okay, so I mean, like, even with that disadvantage, right, the main thing that you're going to have to be able to learn in here is you just need derivative, and you're going to be fine, right? You're going to be fine. Okay, perhaps another thing that we should kind of also try and look at is, say for example, something like this, arctangent. Well, no, even not even that's cube root. Cube root should work. Look at this. Let's try and see this value. Say for example, we have a equals 1. A equals 1. What we're going to see in here is negative 2. Okay, we'll put that in, negative 2, and then let's put it to negative 2. It will now be 16. Okay, 16. Oh, sorry. Here pala, it's 4. 4, and then what will this be? Before, then gonna see negative 8, and actually diverges here, right? And the thing about this now is that you just need to be very careful about, well, if your values are going to get larger or smaller, or to if it's going to oscillate, right? And at this point, like, if you're going to see this unfold, you can put a stop to this and say, well, this is not gonna work. Clearly this is not going to work, so you might need another kind of method in general, right? So say for example, maybe we can change the starting point, maybe 0.5. What about 0.5? It's still going to go to negative 1. It's going to go to negative 1, and if this is negative 1, this will become positive 2. Then it just oscillates back and forth, back and forth. Well, you're not gonna go anywhere, right? What about something like, I don't know, 0.01 or 0.02? It will just double itself. So it's not going to be great talaga. So perhaps cube root of x is one that slays the Newton-Raphson method, but well, this is quite rare in this sense. Maybe x raised to 5 also will not work. Also will not work, I don't think. Not gonna work, right? But notice, hopefully you notice that it gets very, very sketchy in here, especially, right? Notice that this becomes more of a straight line the closer and closer you get to zero. So maybe the Newton-Raphson method just doesn't like this this just doesn't like this kind of progression. So there you go, right? It's not gonna do well in these kinds of scenarios, right? Let's say for example ln of x, right? And ln of x, well, it's gonna be here. So let's try this out. What if you arrive at 2, right? It's gonna be at 0. Okay, try this out. 0.61371. Okay. Let's put this in here. Okay, I mean, it's going to arrive at that answer 0.91344. And yeah, it's gonna get pretty close to 1. Yeah, very quickly. So there you go. So it's only for very select kind of equations. There it is, right? It's gonna go to 1. Okay. So I mean, like, that is all there is to know, I suppose, about these 5 methods. So in your upcoming quiz, of course, you're gonna have your Excel sheet with you, right? And in the quiz, right, I'm gonna have to ask you possible manipulations for, let's say, for example, the fixed point iteration. Maybe I will ask you about how many iterations it needs, how many iterations you're going to need for a specific kind of error, right? And basically that kind of thing is the kinds of questions I will ask for this part of the exam. Right? Of course, next we will go with numerical solutions for differential equations. So in that case, I will see you in the next part of this series, and this is the last part for this condensed version of MEADMAT for now. So thank you very much. I'll see you then.